Question 1. The determination of compound structure by using mass spectrum, IR, carbon NMR, and photo NMR. Let's get into the question.
Good day, Doctor. I'm Usha S. Ramesh, ID number S821088. So now let's see the solution for the question 1 of IR spectrum. So this is the IR spectrum of the question 1. I have highlighted the main four significant absorption, where at the very first that is obvious was a 3200, which has the strong and broad, that has the bond of OH, which we can identify easily, that is alcohol. It is alcohol, but what substitution it is, that is also as answer. So at 1000 to 1020, which is at this, there is a type of bond that is a CO bond, which it indicates the primary alcohol. So we can identify that, we can also confirm that in this unknown molecular structure has the alcohol presence. So at the wave number of 3000 and also 1500, both have the sharp peaks, which 3000 shows the unsaturated sp2ch and also 1500, so the C double bond, C bond. These both shows the characteristics of the benzene ring. So we can say that through this IR spectrum and these wave numbers of 4, we can know that two wave numbers indicates the alcohol, which is primarily alcohol. Another two is indicates the characteristics of the benzene. So we can have a clue that there is a presence of alcohol and also the benzene ring.
Good day, Doctor. I'm transitioning with student ID SA21010. So this is the mass spectrum of question 1. I have labeled 5 significant peaks for us to identify the compound. From the spectrum, we know that the molecular ion peak is located at mass to charge ratio equals to 108. So from this, we can know that the molecular weight of the compound is 108. Previously, from the IR spectrum, we already identified the presence of aromatic ring, OH bond, and also CO single bond. So we can assume that there is at least one oxygen atom in the compound. The peak at mass to charge ratio of 91 has indicated the loss of 17 mass units, which is counted as the loss of 1 oxygen and 1 hydrogen, while the peak at mass to charge ratio equals to 77 indicates the loss of 31 mass units, which is also counted as the loss of 1 carbon, 3 hydrogen, and 1 oxygen. Therefore, as we assume there is an OH bond, the two peaks have fragment loss of OH and CH2OH. For another two peaks at mass to charge ratio of 107 and 79, they are both the trophylion ions formed due to ring expansion. So we can see the structure of trophylion ions. From the previous slide, it can be confirmed that there is one oxygen atom in the compound. At this stage, rules of the things can be used to determine the formula of hydrocarbon part. After subtracting the mass of oxygen, we obtain the rest of mass in 92. Using the rules of the thing, we calculate the N and M as 7 and 8. So the compound is having formula of C7H8 for its hydrocarbon part. Then by adding with the oxygen, the molecular formula of the compound is C7H8O. So this is the identification of the molecular fragment for each peak in the mass spectrum. As what is mentioned before, the 108 is the molecular ion peak. By grouping the aromatic ring with the alcohol part, CH2OH, we obtain the molecular formula of C6H5CH2OH. The peak at mass to charge ratio of 91 with loss of OH radical is the molecular fragment with formula of C6H5CH2, and the peak at mass to charge ratio 77 with loss of CH2OH radical is the molecular fragment of only the aromatic ring with formula of C6H5. The rest two peaks are detected to be the trophylion ions due to ring expansion.
Question 1. NMR spectrum, carbon NMR. At the ppm of 65, there is a functional group which is RCH2OH, where CH2OH attached to another compound. Another chemical shift is at 125 ppm to 145 ppm, where there is a 4 peak, shows there is 4 carbon attached to a aromatic ring. At NMR spectrum, photo NMR, at ppm of 7.2 to 7.4, there are multiplicity of singlet in integration of 5, where it shows there are 5 hydrogen uh, are attached to a aromatic ring, which are also known as mono substitute, which is not coupling to any of the compound. Second, at 4.6 ppm, there is a multiplicity of singlet. Integration of 2 shows a disulfide CH2, which is not coupling. And last, at 2.3 of multiplicity of singlet, the integration of 1 shows a compound of OH, also shows a broad OH peak there. Next, the photoenema given a monosubstituent benzene ring contain of 6 carbon, 5 hydrogen and a CH2 and a peak match that OH. From here we know there is a CH2OH attached to a benzene ring, where by looking at the photoenema we know at a 2.3 ppm there is a compound OH that is attached to this compound, and the second at the point of 4.6 ppm we know there is a CH2 CH2 disulfide uncoupling, and by looking at the ppm of 7.2 to 7.4 we know there is a benzene ring also attached to this particular compound. For the question 1, by looking at all the spectrum, we finalize the compound that the structural formula is CH2OH attached to a benzene ring contain of 6 carbon, 5 hydrogen, and the molecular formula is C6H5CH2OH. The name of this compound is benzylene alcohol, or also known as phenylmethanol.
So this is our question 2. The UV spectrum of this compound shows only N absorption. Determine the structure of the compound. We can see that in this question it shows several graphics, including the mass spectrum, IR spectrum, photon and carbon-13 NMR. For the solving details, we will continue at the next few slides.
Question 2, UV spectroscopy. The UV spectrum of this compound show only a N absorption, where even with the N absorption, we know it's actually support identification of the structure, where a simple ester have a weak N to anti-pi transition near to the solvent cutoff point. By using this particular absorption, we know this compound could be a simple ester itself. Question 2, mass spectroscopy. From the spectrum of mass, we know there is a molecular ion peak of 102, which is also the molecular weight of this particular compound. Peak at the M mass of 57 shows the loss of 45 mass unit, and the peak of 29 shows the loss of 37 mass unit. So for the molecular identification, we have to use the rule of 30, where there is not given any molecular formula. We have to assume a molecular formula by using the rule of 30. So for the rule of 30, we know N equals to molecular weight divided by 30. From that we got 7, which also having some reminder. So for the uh, calculation of M, we have to do a reminder calculation, where R equals to molecular weight minus weight N times 30, where we know we get 11. For the M calculation, we have to plus 7 the N and R to get the M. So M is equals to 7 plus 11 to get the molecular for the M 18. So the molecular assumed to be C7H18. So for the MS 102, we know the molecular fragment can be C7H18 or C6H14 or O, or also can be C5, H10, and O2. For the mass at 57, we know the molecular fragment can be C4, H9, or C3, H5, and O. And last, at the 29, we can assume the molecular fragment can be C2, H5.
So let's see the IR spectrum for the question 2. So from this spectrum, we can identify three wavelengths. So very first is 1740, which shows a strong and also sharp peak that represent the bond of C double bond O, which indicates the carbonyl. So next, we can see over the peak around 1200, there also a sharp peak which shows the bonding of CO bonding, which we can also identify the presence of the ester. Around the wave number less than 3000 at this, there is also a peak was depicted. It has the bond of sp3ch, where it can be also known as the aliphatic ester. Now we need to recalculate back the molecular formula. This is because we got to know the presence of oxygen from the IR spectrum. So previously from the from the mass spectrum, we got to know the MZ value is 102 and the molecular formula was C7NH18. Now we need to include the O in this molecular formula. So for that, we need to use the 102 minus with 2 oxygen atoms value, which is 16 times 2. We will get the new molecular mass, which is 70. So this value will be used to find the molecular formula for the hydrocarbons. So for that, we need to use the rule of 13, which is CnHm. So the 70 will be divided by 13 to get the value of N, which is 5. And then the R value will be calculated for the M calculation, where 70 minus 5 times 13, we will get a 5. So the M will be N plus R, which is 5 plus 5 equals to 10. So now the new molecular formula is C5H10O2, where the C5 from here, H10 from here, and O2 from the oxygen atom that we gain from the IR spectrum.
This is the carbon-13 NMR of the unknown compound. There are 5 peaks in the spectrum, meaning that there is totally 5 carbon atoms in the compound. For the peaks at chemical shift of 10, 15, and 28, they are the characteristic of sp3 carbon. For the peak at chemical shift of 60, it is the carbon that is neighboring with electron withdrawing group. In this case, it is the carbon attached to a single bonded O. And the last peak at chemical shift of 174 is the characteristic of carbonyl group, and at this value is the C double bond O in the ester. Now continue with the proton NMR. At this stage, the proton NMR should provide confirmation on the structure of compound. There are totally 4 peaks in the NMR spectrum, indicates that there are 4 types of proton in the compound. By analyzing all the peaks in the spectrum, we can determine the number of protons in each type, which is in the ratio of 3:3:2:2 from upfield to downfield. This number adds up to 10 total hydrogen atoms in the formula. Then using the splitting pattern on the peaks, the structure of the compound can be identified. So this is the structure of the compound. CH3, CH2, COO, CH2, CH3. Each hydrocarbon group is distributed according to their splitting pattern and chemical shift. The quartet at 4.1 ppm and triplet at 1.3 ppm results in higher chemical shift than the quartet at 2.4 ppm and triplet at 1.1 ppm. This is because the CH2 group at 4.1 ppm and CH3 group at 1.3 ppm is attached to and being nearby an electron withdrawing group, which is an oxygen that is single bonded with a carbon. Hence, for the finalization of the compound structure, through the analysis of UV, mass spectrum, IR spectrum, and NMR spectrum, we can conclude that the unknown compound is an ester with molecular formula of C5H10O2 and the structural formula shown in this picture. It is an ester called propylethanoate. Thank you.
So this is the question 3 where we need to deduce a structure of a compound with the molecular formula C3H7NO from the following spectral data that they given. So from the UV they already given us the lambda max and also the maximum absorption. For the IR they already listed for us around 4 significant absorption. For HNMR 3 chemical shift, and they for the CNMR which is off resonance potently coupled they mention around 2 informations.
For question 3, UV spectroscopy, the given wavelength 230 nm at the absorption of 10,500. The absorption at 230 nm and the absorption 10,500 is a characteristic of conjunction, where the overlap of an p orbital with another cross of adjacent sigma bond.
This is the IR spectrum of question 3. There are 4 absorption peaks in the spectrum. The first one at wave number of 3428 indicates the presence of NH bond in amide group. The second one at wave number of 2941 to 2857 indicates the presence of sp3ch bond. At the third peak with wave number of 1681 is due to the vibration of carbonyl group in amide compound. And the last peak with wave number of 1452 is the scratching of CC single bond.
So now let's we see the HNMR data for the question 3. They already given us the chemical shift values, multiplicity which also known as the splitting pattern, integration. So now our work is to find the assignment because we need to arrange the unknown molecular structure. So if you see all the 3 values, they already given that singlet, which means we cannot use the n plus 1 because n is equals to 0 due to there is no neighboring. So we have to use the integration values to find the assignment. So this both cases has 3H, which means the group should have 3 hydrogens. So obviously we can know that is there are methyl groups. So one methyl group here, another methyl group here. Why it is higher? Why this methyl group has higher compared to this one? This is because this CH3 could be attached with another with atom which is not C. That is why it was downfield deshielded compared to this methyl group. So at here the chemical shift for 8.13 the integration is H, so the assignment is H. So we need to find the H was attached with N or not, because in the molecular formula we can has a clue that it could be attached with the N. So let's see the CNMR. They given two informations, which is 2 quarters and also 1 singlet. Quartet means 4. So now we can use the n plus 1 rule, where the n, to get the value of 4, the n will be 3. So for the 3, definitely we can know that the CH3, which has 2 methyl groups. So from the HNMR, we already to CNMR, we already confirmed that they are 2 methyl groups were present. So there is also mentioned that one singlet, which is 176. So we can refer the NMR chemical shift table, where the 176 is over here. If you see here, it is represent the C double bond O, which shows the carbonyl group. So that is how we can find the data from the CNMR. So now let's we finalize the molecular structure from the given data. From the UV we got to know it is a conjugated, so it indicates the presence of the double bond. From the IR, HNMR and also CNMR we got to know the presence of the methyl groups and H and also C double bond O. So from all this data, when we arrange into a molecular structure, this is how it could be. Okay, as from the CNMR and also HNMR, we already know that there are 2 methyl groups are present, one here, another one here. Okay. As I told in HNMR, this methyl group 2.7 methyl groups is will be attached to another atom which is not C. So as I told, it was attached with the N. Okay, here the CH3 is 1.9. As I told, it will be in the corner. This C methyl group is downfield deshielded compared to this CH3 due to the presence of the N. As the same case goes to the H which is singlet, was directly attached to the nitrogen, which is a trivalent atom. That is why it shows the chemical shift value is 8.13. That is how this way we have to arrange the molecular structure. Next, the C over in the middle here, the C double bond O, which present the carbonyl group. The C is arranged in the middle between the C and another N. Why? This is because the C NMR is already mentioned that it is a off resonance proton decouple. If like that means the value is 176, and if they also mentioned that one singlet. Okay, in the case of off resonance, okay, if the off resonance, when the splitting is singlet, they won't attach with H. So it is correct when we arrange in the middle because it was attached with a C and also N. That is why we arrange in the middle. Okay, to clarify again this molecular structure, we can use the DBE theory also, where for this case, the type of DBE is the type B. This is because there is a presence of nitrogen, which is a trivalent. Okay, to calculate the DBE, we can extract the molecular formula values, where this is the formula. The X represent the C, Y represent the H, and Z represent the N. So in DBE, normally we will avoid the O values. So once we calculated, we will get the value 1. And yes, there is a 1 double bond in the molecular structure where in the carbonyl group. So that is how we need to find the molecular structure for this unknown unknown molecular formula for the question 3.